You know that sinking feeling. You spend hours, maybe days, designing a circuit, carefully assembling the board, and you power it on, and you get absolutely nothing. It's totally dead. You check your solder joints, you reread your code, but the real culprit is something you couldn't even see. Today, we are going to master the science of electrostatic discharge, or ESD, and build a workstation blueprint that actually keeps your hardware alive. Here is our roadmap for today's explainer: the invisible threat, the anatomy of a zap, the 4 rules of ESD, a practical workstation walkthrough, a massive gotcha about sitting down, and a quick recap. Okay, let's jump right into part 1, the invisible threat. So when your board mysteriously flatlines on power up, you're usually looking at electrical overstress, or EOS. ESD is a huge player in that EOS family, right up there with lightning strikes and electromagnetic pulses. And here's the crazy part. When an integrated circuit dies from ESD, there's no dramatic smoke, no blackened burn marks on the package. It is literally a microscopic assassination. And this isn't just an annoyance for hobbyists. We're talking about a massive industry problem. Electrostatic discharge destroys product yields, costing the industry literally billions of dollars every single year. It creates these awful, latent unreliability issues. That's exactly why modern electronics manufacturers treat absolutely all semiconductor devices as highly ESD sensitive. No exceptions. Moving on to Section 2, Anatomy of a Zap. So what's actually happening here? Electrostatic discharge, at its core, is just the sudden transfer of static charge between objects at different electrostatic potentials. Static charge is simply unbalanced electrical charge just sitting there at rest, a deficiency or excess of electrons. But when those charges find a bridge to a different potential, they move, and they move ridiculously fast. To really visualize this, think of electrical potential exactly like water pressure in a massive storage tank. As you move around your lab, you're effectively acting like a pump, filling up your body's water tank with immense pressure. Now, your delicate integrated circuit, that's a tiny, fragile glass pipe connected to a grounded drain. The second your charged finger touches that IC, it's like throwing open a massive valve instantly. The resulting rush of high-pressure water creates a violent water hammer effect that physically shatters those microscopic glass pipes inside the silicon. That water hammer is what kills your chip. Just to put that pressure into perspective, simply walking across a synthetic carpet on a dry day can generate up to 20 kilovolts of potential on your body. Imagine a water tank pressurized to 20,000 psi. That is the incredible, invisible force your delicate little components are up against. All right, let's get into Section 3, the 4 rules of ESD. Every single ESD event strictly follows a 4-stage sequence. First, charge generation, usually from friction or contact. Second, charge transfer. That's the moment the valve opens and potentials equalize. Third is device response, which is how the circuit tries to handle that massive rush of charge. And finally, 4, device failure. This can be a hard failure, where it's instantly dead, or even worse, a latent failure, where the chip survives but is critically permanently weakened. Now, charge generation is governed by the trio-electric series. This basically dictates which materials generate positive or negative charges when rubbed together. Stuff near the top, like air, human hands, or rabbit fur, gives up electrons and goes positive. Stuff near the bottom, like Teflon, silicon, or PVC, hoards electrons and goes negative. So if you're rubbing your hands against polyester, you are generating a massive charge imbalance right there. Keep in mind, those charges can trigger a discharge in a few highly specific ways. We always think of the first one, a charged person touching an IC. But consider the second point. If a device picks up a charge, say, from sliding around inside a plastic bin, and then it touches a grounded surface, boom. It discharges its own water tank into the ground and destroys itself. Also, an ambient electrostatic field can literally induce a voltage across a dielectric until it breaks down without anything even touching it. Let's bring this to the real world. Section 4, Practical Walkthrough for your workstation. So, the whole point of a static control wrist trap and foot grounder isn't to magically stop you from generating a charge. You're going to move around. The goal is to provide a continuous, safe, high-impedance drain. Going back to our analogy, it acts as a tiny, controlled pressure relief valve that constantly bleeds off the water pressure before it ever gets a chance to build up to that 20,000 volt mark. Here are your absolute do's for your workstation. First, treat everything as static sensitive, period. Second, Always touch a common ground point before handling your assembly. Third, wear that grounded rest strap. And fourth, this one gets overlooked all the time. Keep your relative humidity at 40% or greater. Why? Because moisture in the air creates a microscopic conductive film on surfaces that naturally bleeds away static charges. Dry air is a harsh insulator. Humid air is a gentle pressure relief valve. And here are the critical don'ts. Minimize your movement, because movement equals friction, which equals charge. Don't touch delicate pins or traces directly. Always hold the PCB by its edges. And listen, if you just scooted your chair across a carpeted floor, or if you're actively feeling static shocks when you touch a doorknob, step away from the bench. Your water tank is fully pressurized, and you are currently lethal to your electronics. Which brings us perfectly to Section 5, the sitting danger gotcha. This is a really common pitfall. You might actually think sitting at your workbench is safer. After all, we just said don't move around a lot, and sitting definitely feels more stable than pacing around. But changing your posture fundamentally alters your body's electrical properties. Here's the gotcha. By sitting down, you can actually store twice as much charge. Because your body suddenly has way more surface area closer to the floor and the chair, your physical capacitance doubles. Going back to our water analogy one last time, sitting down doesn't just increase your water pressure, it literally doubles the size of your water tank. So if you generate a spark while sitting, the volume of that violent water hammer is twice as massive. It's twice as dangerous to your ICs. All right, let's wrap this up. Section 6, final recap and outro. Let's lock in the 3 main takeaways. Number 1, never forget the water hammer. ESD is a rapid, destructive equalization of potential that will physically shatter your components. Number 2, respect the materials. Charge generation is governed by the triboelectric series, so keep synthetics, cheap plastics, and regular tape completely off your bench. And number 3, ANSI standard workstation setups are not optional. Ground yourself constantly and keep that lab humidity at or above 40%. So the next time you pull a microchip out of its protective packaging, ask yourself, is my workstation a safe oasis, or am I about to unleash a 20,000-volt water hammer on a microscopic city? Control your environment, respect the materials, and keep yourself grounded. If this explainer helps save your next integrated circuit, make sure to hit subscribe for more hardware survival guides. See you next time.